All right, today we're going to talk about Chapter 9, Lesson 1 multiple representations of functions. There are different ways to represent functions. We have the verbal, it tells a story, a graph, describes a picture of what's happening, an equation where we're using some algebra. So, some objectives for today are to solve problems by using the various representations of functions. We've got verbal, equation, table, and a graph. What can we say about this situation? You notice our x-axis here has hand washing number of times people wash their hands per day, and on the left, our y-axis is the sick days per year. If you look at the data points, it looks like the more you wash your hands per day, the less sick days you have, the less sick days per year you take. If you notice right down here at these points, people that wash their hands over 20 times a day, on average, have less sick days. Let's take a look at another example. The amount of sleep needed per night by age. Over here we've got your hours of sleep. Y-axis is your age. What could you say about this graph? I would start by saying it appears the older you get, the less sleep you need. So we got different ways to represent a function. We got verbal, tells a story. Graph is a picture. The equation using our algebra. So let's take a look and see if we can match a situation with its corresponding graph. So take a second, take a look at these graphs, take a look at the descriptions, and see if you can match up the graphs correctly. Number one, a train approaching its destination. Okay. Something that's stopping at a constant speed, approaching its destination, I'd go with graph C. The temperature increases during the day, then dramatically drops by late evening. Well, we're looking for a graph that's going to increase and then drop dramatically. I'd go with graph D. A helium balloon is released by a child on a calm day. Okay, I would go with graph A. And let's see, movie ticket prices increase at a constant rate. That would be graph B. We can use this stuff to solve some problems here. So taking a look at this, here's the verbal description. An amusement park manager estimates daily profits by multiplying the number of tickets sold by 20. This verbal description is useful, but other representations of the function may be more useful, such as the equation here. Profit equals 20 times n, where n represents the number of tickets. Or you could use a table where we have some values, where if you sold 50 tickets, there's a profit of $1,000. If you sold 200 tickets, profit of $4,000. Sometimes a table is useful. And lastly, you have a graph, and you can see this graph is going to continue to increase at a constant rate of 20 times the number of tickets. So let's take a look at an example where we can come up with these three types of information. So here we go. We got Janet is rowing across an 80-meter wide river at a rate of 3 meters per second. Represent the distance Janet has remaining before she reaches the other side. When will she reach the shore? Hopefully you didn't see that. We can create a table if we think she's rowing across an 80-meter wide river at a rate of 3 meters per second. So if she's at time 0, okay, she still has 80 meters to go. And after 1 second, if she is going 3 meters every second, that's what meters per second means, she will get 3 meters closer to the shore. So after 1 second, she would be at 77 meters. And it's going to continue this way. After 2 seconds, she'd be at 74 seconds. And after 3 meters, 71. And after 4, 68. So here's a table that represents our values. So I'm going to switch slides here, but same problem. Now let's think about what would a graph look like. Okay. Well, we know that she's going to start at, let's get rid of this line here. We've got a couple of points here. She's going to start at 80 when the x is 0 from our table. Okay, so if we go back, we look at our table, we've got 80 times 0, distance 80. At time 1, we have a distance of 77. So we can kind of estimate that. Mine's not going to be perfect here. At 2, we've got 74, and so forth. If we kept going with this table here, and we got to 5, that'd be 3 more, so we'd be at 65, and at 6, we would be at 62. So if I go to my graph here, I look at 6, that's about 62. It should be above there a little bit. Right here. Okay, you can see this is going to be a nice line that's going to start at 80. It's going to go down at the same rate. So let's see if I can fix that here. It's going to end right around here somewhere. Okay, it's a constant rate. She's going at the same rate throughout the whole river. Okay. If we try to write an equation here, our equation, we know that we start at 80. That's that y-intercept. And we subtract our distance of 3 meters per second. So that is where our 80 minus 3t comes into play. And asks, when will Janet reach the shore? Well, she's going to reach the shore. Let's use this equation. That's going to help us the most. Table would take us forever to figure that out. The graph, we know we can get close, but we're not exact there. But the equation, we're wondering when we have a distance of 0. So we're wondering what our time would be. So to solve this, let's subtract 80 on both sides. So we have negative 80 equals negative 3t. Divide by negative 3. Divide by negative 3. And our time equals, if we take negative 80 divided by negative 3, we're going to get a positive answer of 26.6 repeating. So she will reach the shore after 26 seconds. So again, we got different representations. We got a table, graph, and an equation. Let's take a look at this example. Ignore this writing down here. This is for a different example. I'll delete it. Get it out of your way. Okay. If we tried to create a table of this example, you got an investor buys a property for $1,000. Experts expect the property to increase in value by about 6% per year. Use a table, a graph, and an equation to predict the number of years it will take for the property to be worth more than $150,000. Okay, well, the initial value is $1,000. And if we try to figure out after 1 year what it's going to be worth, well, we need to take 100,000 and multiply it by 6%. 6% on the calculator is 0.06. So if you take 100,000 times 0.06, that is going to give you $6,000. Which seems kind of low, but that is how much the value will increase. So if we gain $6,000, after 1 year, the property is worth $106,000. Okay? Each year it increases by that. So for year one, it's worth $106,000. We're going to take that number and multiply it by 0.06. And we're going to get $6,360. So we're going to add this number to my 106,000, what it initially was, to get 112,360. And you might ask yourself, is there a faster way to get that? There is. Okay. So in year two, if we take this 112,360, multiply it by 1.06, you would get 119,101, where you don't have to do, well, 0.60. You don't have to do any extra adding. So after 3 years, we can round that up, it's worth $119,102. Take that number again, multiply it by 1.06, and after 4 years, it's worth $126,248. Now, graph is easy. Just take these table values and plot them on the graph. As you can see, it is starting to grow a little bit more. It's not necessarily linear because it's not going up by the same value every time. But it is, you are gaining value. So we're wondering, when will it be worth more than $150,000? Well, let's continue to fill out this table. So year 5, how much is it going to be worth? We'll take your 126,248 times 1.06. You're going to have 133. Let me erase that. 133,822. Multiply that by 1.06. So in year 6, it's worth 141,852. Multiply that by 1.06. And in year 7, it is worth 150,353. So if I continue to fill up my table, I will find out that in year 7, so it takes 7 years for this property to be worth more than $150,000. Here's your assignment in case you haven't seen it on Canvas.